Welcome to Business Analytics. This is Hari Rajagopalan, and we'll be covering this session on discriminant analysis for you. So we have finished descriptive analytics and we are in predictive analytics right now. And you would have probably listened to all the sessions in regression. And remember, in regression, your independent variable or your predictor can be both continuous or categorical, and we've talked about how to handle it if it's categorical. But your dependent variable all the way up to now is continuous. But if you are going to deal with a dependent variable which is categorical, then the statistical technique that uses information from a set of independent variables to predict the value of a discrete or categorical variable is called discriminant analysis. The goal is to develop a rule for predicting which of the two or more predefined groups for a new observation belongs based on the values of the independent variable. So let's take examples. You can look at credit scoring, new loan application, whether it's going to be a default or whether they're going to repay. Insurance rating, will the client be high, medium, or low risk? Where there is a transaction, credit card transaction, is that a fraudulent transaction or a normal transaction? So types of discriminant analysis, we are going to look at two group problems where we can use regression. We are not going to look at problems which are greater than 2 because we cannot use regression. We'll talk about why we cannot use regression, and we'll talk about what we can do and the tools which are there, but we are not going to do example problems of this. Okay, so let's move on to the next slide. So we're going to look at an example of Acme Manufacturing. Acme Manufacturing is that all employees are given a pre-employment test measuring mechanical and verbal aptitude. Current employees have been classified into one of two groups: satisfactory, which is group 1, and unsatisfactory, group 2. We want to determine if the two groups of employees differ with respect to their test scores. If so, we want to develop a rule for predicting whether the new applicants will be satisfactory or unsatisfactory. So here's the data. We have 20 employees here, and here there are 11 in group 1, which is satisfactory, and here where their mechanical and verbal scores, and here is group 2, there are about 8, and then here are their mechanical and verbal scores. So remember, what they have done here is they've already hired these people, right? And then they've had mechanical and verbal scores for these people, and then they looked at it and then they classified them as, here are the employees who are satisfactory, here are the ones who are unsatisfactory. Now using this, they want to build a model. Okay, so let's look at, if we plot this, we can see that here in blue are the satisfactory employees, and then here in pink are the unsatisfactory employees, and here is their centroid. And literally it's easy to see from visually for human beings that here's where the cutoff is, kind of. Where is this cutoff going to be? Okay, but it's hard to build a model, and we'll talk about the process of building a model. So the first step to build a model, and we'll do this in Excel, but I want to show you what we are doing before we get into Excel. We are going to build a regression equation. This here, group 1, this is your dependent variable. We are deciding whether things are going to belong to group 1 or 2. Remember, it's categories. And then these are your independent variables. And we build our regression equation based on that. So we go ahead and get a regression equation. And then we get our classification rule basically by generating a discriminant score based on this regression equation. So we have group 1, which is distributed this way, group 2, which is distributed this way, and if we pull a cutoff point, here are the number of people, percentage of people who are actually in group 1 who will be classified as, who are in group 2 who will be classified as group 1. And then here will be another cutoff. Here is another error. Here is the percentage of people who are actually belong to group 1 will be classified as group 2. So here this darker blue is the percentage of people who you say are satisfactory but actually are unsatisfactory. And here are the group of people who you say are unsatisfactory but are actually performing pretty well. So this is essentially the regression equation. Well, I'll show it to you in Excel. And we use this to build the discriminant score. And then here will be the discriminant score. And here we'll classify based on the discriminant score. And what we are doing here is group 1, we take from 1 to 11. We find the average here. This will give you the centroid. For group 2, here is the average. This will give you the centroid of that. And here will be the discriminant scores. And we can take the average of that and build a rule. So let's get, so that's your discriminant score. So let's, and the discriminant score actually results in this cutoff value, and that will give you your classification. Okay, so let's get into Excel right now, and we'll see how this is, how we can do this. Okay, so here is the finished form, but let's start from scratch. Let's start with just, this is the data which will be given to you, right? So this is all you have. This is the data. And the first thing to do would be to build a scatter plot, and you select data and you go, your X values here is your, for group 1, and your Y values are, this is again for group 1, and you can say that is your group 1, right? So you can say series name is group 1, and then for group 2, your mechanical aptitude starts here, and Y values is your verbal aptitude, and that's your series name is group 2. All right, so here we go. And if you like, you can, if you want to magnify this, but remember, every time you magnify this, you need to let people know that you're magnifying it. So this will then be minimum of 25. And then here, format axis, this will be 25. And that should magnify it. And you will be then able to draw a curve which actually shows you where your circles are, right? And therefore then you can find the cutoff point here. Okay, so that's pretty much what we're doing with visualization. So the first step is to go ahead and do data analysis, regression, and your Y range is this, your X range is this. You got labels, confidence, and you can go put the output range somewhere here. So it's all the way away. And you got an intercept and then the slope here, right? It's all set up here. So now you can then build a discriminant. You can kind of say here is the discriminant score. And the discriminant score is, you're going to have intercept plus mechanical F4 multiplied by your mechanical score plus verbal multiplied by your verbal score, right? So this would give you your discriminant score, and you can copy this all the way down. So let's go ahead and format, make sure we stick to the format. This will be, so we also can get group 1 and group 2 averages. So get the average this here, average of group 2. So we know where the center spots are, the centroids are. So obviously group 1 is 39.9 mechanical score and 37.6. That's the center, whereas here it's 34 and 33.7, right? And you can now copy and paste the formulas to get the centroids here. And let's go ahead and get that taken care of. Here we go. And then again, we can format it. And so the cutoff point is the average of these two, right? Because if you're going to weight group 1 and group 2 equally, then it's 1.479. That's your average value. So this is your cutoff, right? And so you can now classify with an equation which says if this value is less than this, then you have 1, otherwise you have 2. And so you can go ahead and run the classification. Oops. And that should be F4, and you can see if I forget to do F4, that creates problems. And there you go. So here we have some error. There is an error here, and then error here. Oops. Sorry about that. So error here and here, right? So as you can see, 2 out of the 12 or the 11 have been misclassified for group 1, and 2 out of the 8 or the 9 are misclassified for group 2. So if we go back here, we can kind of see we need to create something called the confusion matrix. So you have group 1 and group 2. This is the actual, and this is what is predicted. So you have predicted. And you can use the COUNTIF function. So I've said COUNTIF, and I've selected this whole thing if it's 1, right? So it counts 9 here, and this the same thing COUNTIF if it's 2. And so 9 out of group 1 have been counted correctly, predicted correctly, and 2 of them have been predicted wrong out of the 11, which gives you an error of 18.2%, right? Similarly here, group 2, use the COUNTIF function, right? And again here, you use the COUNTIF for 2, and then here, 7 out of 9 is correct, 2 out of 9 is wrong, so that's 22%. So here is a new group of test scores for whom you have not been given these values. So these don't exist. You just got this new group. Here's the mechanical data. You want to whether you should hire them or not. And if you're going to use this model, you essentially get the discriminant score, and you say, all right, based on the score, you're going to hire 1 and 2 and 4, and you're going to not hire 2, 5, and 6, right? Some of you might be wondering why, as the scores grow lower, you are hiring. As the scores go higher, you're not hiring. Notice that group 1 are the ones you want to hire. Group 2 are the ones you don't want to hire, and therefore the higher mechanical and verbal scores are. That's why their coefficients are negative. The lower the overall score is. Okay, so the people who are unsatisfactory have a higher score. People who are satisfactory have a lower score, and the reason is because satisfactory is 1 and unsatisfactory is 2. If you switch this out where this is 2 and this is 1, then these will be positive, and then the satisfactory people will have a greater score. So hopefully everybody's got that. So back to our PowerPoint, and the cutoff value you talk about, let's use some fancy words right now. So for data that is multivariate normal with equal covariances, the optimal cutoff value is you're going to get the discriminant score of group 1, the average discriminant score of group 2, and you're going to divide it by 2. So in our example, you basically get 1.479. Even when the data is not multivariate normal, this cutoff value gives pretty good results. So what the heck is multivariate normal? So if you have a normal distribution, you have a bell-shaped curve, right? When you have more than one variable, so if you have one variable and you look at a normal distribution, that's univariate. It's one variable. So if you have more than one variable, that's multivariate. Now you can visualize a bivariate, which is a form of multivariate, which means there are two values. So here is an example of a bivariate normal distribution. So you look at it as a plane, and then here you have this whole normal distribution in this plane. But more than two variables is difficult for us to imagine. Three-dimensional, possibly a cube with this thing kind of jutting out, but it's going to be difficult. So 2 dimensions is probably the best you can do with imagination. So if you have more than 2, then it's going to be difficult to visualize it. So here's what we've got as our confusion matrix, and we kind of have finished treating both groups equally. So both groups have 50% weight. Okay, so let's look at the issues of misclassification, right? When we say things are group 1 when it actually is group 2, or when we say something is group 2 when it's actually group 1. Let's take an example where it makes it very obvious to you. The costs, let's make an example of the costs. What if the classification is you have cancer versus you don't have cancer? And the doctor says, you're in group 2, you have cancer when you don't have any cancer. Or the doctor says, you're in group 1, you don't have any cancer, but you do have cancer, right? So the costs may be higher for one group for the other. It's not the same for each group. Second is, do we know anything about each group? Do we know the probabilities before you have data? Maybe 90% of the people who come into office, or 99% of the people who come into office, do not have cancer. And therefore, do we need to use that kind of information instead of assuming they are equally distributed in the population? So here are some examples. What is the probability that transaction is a fraud before you know anything about it? A priori, and usually it's 2 in a million or something like that. Transactions tend to be fraudulent as they're coming through. They're coming in high volume to a credit card company, but most of the transactions tend to be not fraudulent. So then the errors are, the model says the transaction is fraudulent when it is not.
Bluetooth pairing mode is off.
Or the transaction model says transaction is valid when it is fraudulent. Second, same thing, the cancer, right? So what is the probability of getting cancer for a normal person before you know anything about the person? That's called a priori. A priori probabilities is before you know anything, what do you know about the population in general? And a lot of times we have that information. So for example, in your company, the example with your company, you could say, I know 95% of my employees are unsatisfactory, whereas 5% are unsatisfactory, right? So these are this set of information, both the a priori probabilities and the cost of making the mistake, whether it's group 1 or group 2, need to be taken into account. Okay? So the refined cutoff value is given by this formula, and we'll show in Excel how to calculate this formula. But it's important to understand this is the first part. This is your old cutoff value. So you're going to take your old cutoff value, and then you're going to add, here is how you calculate the pooled variance. And then you're going to add this ratio and then the log. And here there is a formula, but this is your P1, P2 is your prior probability for group 1 and group 2. And then C1 of 2 and C2 of 1 is, you see the definitions here. So here is the example, and we already have this in this example. We are saying 80% of the employees are satisfactory and 20% are unsatisfactory. And we know that the cost of classifying satisfactory employees as unsatisfactory is half the cost of classifying unsatisfactory employees as satisfactory. So remember that doing 2 to 1 is more expensive than doing 1 to 2. So if 1 to 2 was 1, this is half of this, so this would be twice that. So then C1 of 2 is 1, C2 of 1 is 2. You can also use 0.5 and 1, but I like to use whole numbers. That's why I put 1 and 2. Okay, so let's now move to Excel, and let's look at how we can recalculate the new cutoff based on these 8 priorities and the cost of misclassifying. So this would be important and realistic rather than treating them together and as equal. So we're going to take this discriminant analysis and refine the cutoff using the new information we have. So here's the new information we have. 80% of the employees are successful, 20% are considered unsuccessful, and it costs 2 times as much to classify someone as unsuccessful when they are successful as rather than the cost of classifying somebody who's successful as unsuccessful. So remember, we said this is half as much as this. That's why this is 1 and this is 2. So the first thing to do is to calculate your pooled variances. So you want to do group 1 variance and group 2 variance and use this formula to get your pooled variance. The 10 comes from group 1 sample size, which is 11 minus 1. The 8 here comes from 9 minus 1, and you are going to calculate that. Once you calculate the pooled variance, you are going to calculate your new cutoff. And your new cutoff is your old cutoff, that's the first part here, plus your pooled variance divided by the difference between group 1 average and group 2 average, and then this log value, which you see here. So this gives you your new cutoff. And based on your new cutoff, you can then try and classify the values. In this particular case, there is really no change because it goes from 1.4786 to 1.51, and there are no discriminant scores here which are between. So there's not a 1.48 or a 1.49 which will then be reclassified. So in this case, there is no change. And same here, there is no change here, but that's because there's no specific score which would then be reclassified and change this particular error. So for example, if this was like a 1.49, then this would have been classified as 2, whereas in this new class, it would be classified as 1. It would reduce the number of it would actually reduce the number of group 1s which are classified as 2, but it would increase the number of group 2s which are classified as 1 as the cutoff becomes higher. All right. So there is one more example here which all of you can go through. Again, here we have MBA admissions. Here is the GPA of students and their GMAT scores. Faculty have rated them as 1 who are successful and 2 people who are not successful in the MBA program. So these are 30 students, sample of 30 students who admitted into the MBA program. Here are the GPA and GMAT scores, and 1 means successful, 2 means these 15 students were not successful. And you can see where the group 2 is and group 1 is, and you can generate this scatter plot, and that'll tell you where these students are, and you can kind of go through the same steps here of the discriminant score, using the regression equation to get the discriminant score, make the prediction, create the confusion matrix, and then making the prediction for the new data set. You can also go, there's an example where you are asked to refine the cutoff. And here we have, again, it's 80-20. 80% of the students are successful, 20% are unsuccessful. And here's the cost of classifying group 1. Successful is 1.2, and the cost of classifying group 2, which is unsuccessful as group 1, is 1. So this is 20% more expensive than the other one, in which case this was 1.2 and this is 1. And then when you reclassify, you get the new setup. I won't go through this because I've already gone through how to do it here. You can get into the details, but let's get back to our PowerPoint presentation. So we looked at the second example on MBA admissions, and what I would suggest is for you to think about what other examples of classifications you can find in your work environment. And the question comes then is, what if we have more than 2 categories? Now, if we have more than 2 categories, you cannot use regression. But there are other algorithms which are available in the analytics solver. We'll talk about it, but we won't go over it in this class. There are also issues where if the data is not a nice circle, if the group is distributed in an elliptical shape or some other shape, that this measure, what we are using, won't work out very well. And we'll talk about other distance measures called Mahalanobis distance measure. Again, we are not going to get into the details there. So what do we have? What happens if we have more than 2 groups? Let's say we have 3 groups. And let's say A is 1, B is 2, and we kind of assign A as 1, B as 2, and C as 3. And we have 1 independent variable. So we have a classification rule which says, well, here is A, here is B, and here is C. And hey, anything less than 1.5 will be A, this will be B, and this will be C. So this will actually work if you have it set up in this way, because it's kind of linear, right? You have 1, group 2, and group 3. But what if this blue was A was up here in group 2 and B was in group 1? So let's take an example here. So suppose we reassign the group, and now the relationship is not linear, but it's curved like this. Then we can't really figure out how to work this, which is why we cannot use this method, regression method, for these more than 2 groups, right? It's not going to work. And I'll show you, there's an example of a 3-group discriminant analysis problem. And here you can classify them as superior, average, or inferior. So you can have them at 3 groups, and then you can develop a new rule, right? And so if you want to classify the data then as, if you have 7 in group 1, then 5 in group 2, or 6 in group 2, and then the rest. So here is group 1, group 2, and group 3, right? So here is the set. And this would be difficult to do with the regression method. If you are in Excel, and let's move to Excel, we could actually, there is something in Excel which allows us to do it. So let me open up Excel, and let's open up this. So under data mining, here in your analytics solver, you have classification of discriminant analysis, which allows for more than 2 groups, but we are not going to do that in this class. This is beyond the scope of this class. All right, so the method you used, which we talked about, compute the distance, make sure to assign it to the closed group. How you compute the distance normally is by Euclidean distance. We're saying, we are taking x-axis, the point, x-axis value, and then we're saying how far is it from the centroid, and then the y-axis value, how far is it from the centroid, and then we square it, take the square root of them, and then but this doesn't really give you the variances. This works when you have this data is distributed in these nice circles. But what if data is, distributed something like this, kind of elongated along, it's stretched along y-axis, but on the x-axis it's much shorter. So if we have a point which is right here, we know visually we can look and say this belongs to this centroid here, but actually if you look at Euclidean distance, it'll be more closer to C2 than to C1. And so the Euclidean distance measure actually requires the distribution to be, it can't be stretched in any one direction, any one of those axes. So there is a new distance measure, which is called variance adjusted distance, and also Mahalanobis distance measure. Now, all you need to know is that if your data set is not, distributed equally in both axes, you cannot use the Euclidean distance and you've got to use the Mahalanobis distance measure. For those of you who are more interested in this, you can contact me and we can talk more about the details about this, but it is not there for this class. How to calculate is not there for this class, and analytic solver using the discriminant analysis does have an option where you can use this distance measure. With this, we finish discriminant analysis, and we move on to the next topic, and we finished regression here, and we move on to the next topic.